So good afternoon, everyone. I'd like to thank Hugues for being here to a fantastic day, a fantastic symposium day on revisiting chemotherapy. Therefore, I really want to stick to chemotherapy and take you on a journey from clinic to basic and back to the clinic, where we think chemotherapy interferes with cellular senescence, which is the main topic, a cell biological mechanism of otherwise my specialty, being interested in hematological malignancies, in particular lymphoma. Those are my conflicts of interest. So I start very simple. We need, for disseminated malignancies, systems-wide therapy. And I want to focus, after we had heard about other types of treatments, as I said, on conventional chemotherapeutics. Don't want to go into textbook knowledge, but would like to remind us that there is not apoptosis as the one and only typical mechanism of response. There is competition, if you will, and I mean it as I say it, between an ultimate cell death exit from the cell cycle or another exit from the cell cycle, a terminal cell cycle arrest called cellular senescence. What exactly decides in any given cell what fate to take isn't really clear. We can talk about apoptotic priming, work by Tony Letai and others, but it's not really clear what decides. And I will not solve the question, but it's a fundamental question because from an oncologist's point of view, as you will see through my presentation, only a dead cell, a dead cancer cell, is a good cancer cell. I want to make one point which has nothing to do with the rest of my presentation. It's this one, and I think it's actually a shame from all sides, from the clinical point of view, but also from translational research, that this is not recognized. We apply treatments with no sex specificity. We may do this by having, for adolescents, 20 years old patients, different protocols than we have them for frail old patients. But in between, they are not same. Yeah? Patients at various ages have different tumors, even if they are called same, even if they are called AML. AML of a 30 years old patient is not same as AML of a 55 years old patient, but we treat them all same. We treat them by surface or by body weight, and that can't be an answer to the actual metabolism of the drugs and their efficacy in a heterogeneous patient population. This is the low-hanging fruit in my view. Yeah, we can talk about fancy ideas, and I'm certainly the last person not being excited about understanding molecular mechanisms, but here we really lose by not doing a better job and give more adequate dosing in a personalized fashion. So now we are back to my specialty, lymphoma. Aggressive B-cell lymphoma, diffuse large B-cell lymphoma, that standard of care actually hasn't changed for decades. Rituximab, anti-CD20 antibody, and CHOP, polychemotherapy. These patients get cured, they fail. So we have a remaining medical need. And an obvious question when you have such a therapy which can cure 2/3 of the patients, you don't want to give up the standard, but you want to improve the standard, you want to augment. Therefore, colleagues have thought about R-CHOP plus X. Yeah, and here you see it. Oops, a little fast. So here you see what has happened over the last few years. An endless story of failed phase 3 trials. They're all negative. So one has added something to the R-CHOP protocol, studies failed. And I want to point out 2 of these trials because we come back to this later. It's R-CHOP plus minus ibrutinib BTK inhibitor, the Phoenix trial, and R-CHOP plus minus bortezomib, a proteasome blocker, the Remodel B trial. So you see negative trials. So would omics profiling help? Since the beginning of the millennium, we know that DLBCL is actually at least 2 diseases by transcriptome profiling, germinal center B cells, activated B cells, and R-CHOP acts differently on these 2 types. But more recently, colleagues have undertaken deep genomic investigations. They came up with all these genomic subtypes. I'm not going into detail. I just want to point your attention to the MCD and the C5 subtypes, which have some similarity, and you see R-CHOP does really poorly. Yeah? These patients really die with this genomic subtype and don't really benefit from R-CHOP. Okay, but can we revisit those failed phase 3 trials? Both subtypes have, as a common denominator, activated MyD88, a toll-like receptor domain. Yeah, the MyD88 L265 mutation, and that talks to NF-kappa B BDK pathway. And based on this, the idea came up, let's inhibit BDK with a BDK inhibitor, ibrutinib. That's the negative phase 3 trial, now broken down by age, by ABC, and most impressively by the MCD subtype. There's a line. Oncologists love lines in Kaplan-Meier curves. That's 100% event-free survival. The red curve is the MCD. So adding ibrutinib to R-CHOP has a dramatic effect in this otherwise very inferior subtype. That's retrospective analysis, requires confirmation in a prospective trial. A different study looked at the microenvironment, the LME, the lymphoma microenvironment, and subsequently called lymphoma ecotypes. I'm not going into details. I just like to make the point. If one tries to understand the disease in its biological presentation in greater detail and can, for example, pinpoint different T cell states, here CD8 T cells, then you see that these inferior ABC subtypes, now treated with bortezomib in addition, they get lifted up by some 12% or so in overall survival. So tremendous difference if you revisit trials and understand the disease differently. So what's the elephant in the room? It's the functional dynamic lymphoma biology, or the understanding thereof. And we have taken one approach, prospectively unbiased, to get molecular informed information by an R-CHOP plus X approach. And that's these two drugs together. It's ibrutinib and bortezomib as a double targeting approach, proximal and distal in the B-cell receptor NF-kappa B signaling on top of the R-CHOP backbone, and we call this, based on the actual names of these drugs, the IMPROVER-CHOP trial. It's in phase 1, phase 2, IIT. We have an R-CHOP control cohort. The patients do quite well. It's fully recruited, and we can subject these patients or their material to intensive multi-omics analysis, particularly for the reason that we are not just giving this regimen, but we have at start unexposed to any treatment directly in cycle 1. And if there is still remaining disease at interim staging, we have rebiopsies. And we can really look at the disease under pressure of novel therapy or the R-CHOP standard cohort. We come back to this later. Okay, what about cellular senescence in this context? Senescence is considered to be a tumor suppressive program. Oncogenes, activated oncogenes, or DNA damaging therapies, but also targeted therapeutics or immune agents can cause cellular senescence, and that's beneficial. That's a tumor suppressive mechanism. It may even be enhanced by innate and adaptive immune cells helping to clear these senescent cells. But some of these cells may persist, and we have heard about persisters today, and these drug-tolerant persisters or even relapse-driving persisters, they produce via their senescence-associated secretome or SASP inflammation, which is never good for tumors. And they may undergo reprogramming to stemness. We come back to this in a minute. And if they manage to re-enter the cell cycle, if this is not an irreversible arrest, then this could together be a pretty dangerous next step in cancer evolution. Therefore, we try to eliminate these features. Xenomorphics can be applied to neutralize the SASP, the inflammation, or to directly eliminate the senescent cells by drugs which are called senolytics. That sounds all like a good concept, but keep in mind, maybe these cells here, since they crosstalk to the immune system, are needed to maintain immunosurveillance to suppress active outgrowth, and that might be not the best idea to eliminate these cells. We see this maybe in a second. So, in the clinic, the situation is as follows. Patients get diagnosed with a new treatment-naive tumor, we typically choose the standard of care. It is typically chemo-based or containing chemo, and we debulk the disease. And with this, we enter, looks pretty similar to what you have seen in Jean-Emmanuel's talk. We go down to the minimal residual disease. We debulk, we regress, we clonally select, but we also force the disease to enter a state switch. I focus on senescence, therefore I call it not MRD, but minimal residual senescence here. And it's never this, it's only this population here, which is potentially dangerous because that's the population from which the clinical relapse must arise. Therefore, we need to understand the biology here, and we need to do something. We need to consolidate the debulk disease here by state targeting. And it was actually us in a hit one, hit two concept to first time demonstrate 10 years ago that if we provide a hit one by chemo and drive the disease into senescence, then we can exploit senescence-associated vulnerabilities with a second hit treatment to drive a disease now into a second type of cell death here, tunnel-positive disease, and this results in superior outcome. You see in this matched identical pairs that many of the mice carrying senescence-capable lymphomas live much longer if they got the second treatment. It's bifidobacterium. I explain in a second why we used that. And if we do this in a model, you will see this model also in a second, which can genetically not enter senescence. There's no benefit of this second treatment. That's the slide I sneaked in after we heard so nicely from Jean-Emmanuel about chemo-induced metabolic dependencies. It's in this particular paper where we looked in senescence what energetic changes happen. And it's indeed across the board the ATP hunger of the senescent cells to cope with SARS-related proteotoxic stress, which enforces extracellular acidification, oxygen consumption rate, fatty acid oxidation, ATP production. It's all up in senescent cells. And you will see in a second, SUVA minus, we had that slide ago, the genetically incapable lymphomas equally exposed to chemotherapy. They don't show this energetic switch. And you can choose any of an inhibitor of all these pro-ATP generating pathways. You apply the inhibitors and the cells will selectively die. So the first kind of metabolic selection of senolytics, and bifidobacterium is the one you have just seen in the previous slide. So here's SUVA39H1. That's a central mediator of the senescent arrest because these triggers of senescence, they talk to a G1 arrest principle guided by hypophosphorylated RB bound to E2F transcription factors. They sit at their target promoters, which are by and large E2F entry genes. And if you now recruit in senescence and histone methyltransferase, you locally create heterochromatin to shut down these E2F target genes. And a candidate is SUVA39H1, and that's our model that we play with mice having SUVA39H1 alleles lost, and those are the genetically senescence incapable comparators. And here you see in lymphomas, emic lymphomas, 5 days after cyclophosphamide alkylating agent, nice senescence associated beta-galactosidase positive senescence not seen in SUVA minus. And here you see that this is beneficial to have a senescence response because mice being treated with intact SUVA alleles, they have a much better outcome here, progression-free survival, as compared to mice carrying those lymphomas which can't respond with senescence. They can respond with apoptosis, but not with senescence, and therefore inferior outcome. We utilized this knowledge from SUVA-deficient MYC lymphomas and created a signature first in mice and translated that signature as a SUVA signature standing for SUVA-governed good outcome, or SUVA-governed senescence target genes that traveled plaque curve with better outcome in human diffuse large B-cell lymphomas. And then we went back to the MIDI88 mutant diffuse large B-cell lymphomas and looked at those, and we're surprised to see that a sizable fraction, I think that's very evident, is homogeneously positive for the SUVA gene signature. So there seems to be senescence capability, but it it fades away the further we go to the right side, and on the very right side, there's another sizable fraction of these mighty 88 lymphomas, which is P16F deleted, the CDKN2A locus. And if you lose that locus, you lose senescence capability. So looking more deeply into what this means, you find negatively regulated E2F target genes, SARS, senescence, so you find the full featured senescence response, and in particular, stemness, we come back to this, and also T cells. And that's interesting. The first, it's dynamics. It's an interplay between oncogene and therapy-induced senescence, and it pinpoints somehow to T cells. We took these mighty 88 mutant lymphomas, actually we generated them in immumic mice, and noticed they have a high propensity towards senescence, surprisingly aggressive, but always a fraction of the cells, you see the blue cells, are in senescence. So we separated the cells senescence only, non-senescence only, isolated them from immunocompetent recipient mice plus their T cells which were primed by these lymphomas. And while you see here, T cells in co-culture don't do much, cells survive. On this side, the T cells killed 70% of the lymphoma cells away. And if we added a checkpoint blocker, we basically eliminated the entire population. So T cells were primed to eliminate senescent cells. Checkpoint blocker didn't do much over here. That is the adaptive immune surveillance of senescent cells and can be therapeutically harnessed by immune checkpoint blockers. We also noticed that senescent cells are plastic. That's a very important feature of senescent cells. Here we look by gene set enrichment analysis for myeloid features. Yeah? And the underlying transcription factors, JUN, CBP beta, PU1, and the whole population is skewed towards these myeloid transcription factors. Here on single-cell RNA-seq, you can probably appreciate this better. Here is the senescent population upon atramycin, and here you see PU1, highly enriched in the senescent population, or dendritic cells versus B cells up. These cells look, I could show you much more data, but in the interest of time, I don't. They look like macrophages, APCs, have oxidative burst capacity. That's the transdifferentiation of B lymphoma cells undergoing senescence. And we further asked whether this is cell autonomous. We see in purified CD19 positive B cell population, we see the skewing of the dendritic cell signature, same in human DLBCL. We see that this is versus normal germinal center B cells up, and it's also prognostic. We see that in patients which survive, they have more of this myeloid transdifferentiation, as we see that in never relapse as compared to relapse-prone lymphomas. And that's seen here in Kaplan-Meier curves. If we look at mice having this myeloid transdifferentiation, the mice live longer, the patients live longer if they have this myeloid transdifferentiation. Why is that so? Is this APC-like transdifferentiation perhaps a partner for T-cell immunosurveillance? We looked at MHC class 2 is upregulated. If we interfere with the myeloid transcription factor network, we can reduce that. We see more activation markers like CD86, but we also see PD-L1 going up. So it's both. It's more presentation, but also neutralizing or attenuating T-cell function. And if we look in lymphomas which are particularly strong in their myeloid transdifferentiation, CD11b high, CD115, this is a CSF1 receptor, then we see particular high PD-L1. And this translates into, indeed, again, an experiment where we take lymphomas plus their primed T cells, where these T cells can nicely kill the lymphomas and do this particularly well if they were primed not just by a native lymphoma, but by a lymphoma in therapy-induced senescent, and that is paralleled by immune activation markers. For interest of time, I don't show you that we can neutralize this if we block myeloid transdifferentiation. We can further enhance the killing if we add on top an immune checkpoint blocker. Last point. Stem cell plasticity. I already referred to this. Here you see basically the entry experiment, an adult tissue stem cell signature in senescent cells strongly enriched for, but not in equally treated super minor cells, and behind is enhanced Wnt signaling. If we go into lymphoma cells, plate them for colony formation as a stem surrogate assay in a setting where we can short-term turn-on senescence means SUVA39 or P53, the cell senesce. We turn these players off, the cells can be released from the cell cycle block, and then they grow out with a massively superior colony formation capacity as compared to the very same lymphomas where we simply did not turn on this temporary permission of senescence. And this has meaning not only in mice where we have control of the disease by senescence, but at some point when there is outgrowth, these lymphomas enrich for Wnt signaling or nuclear beta-catenin. We see this also in patients. But now we switch the perspective and we look at the question when we have in an untouched cohort, this can be patients, can be mice, this is a clinical trial-like setting, mice get treated, are either cured or relapse, can be retreated and then enter clinical treatment failure, whether in such setting there is hints for senescence-associated stemness. If we isolate those lymphomas, in some of them, the cells simply show resistance in vitro. We can't kill them anymore after they have entered this treatment failure state. Therefore, we call them relapse-prone, apoptotically resistant. But about half of the individual cases, they are surprisingly sensitive when we take them out of this situation. And behind this is, in this apoptotically sensitive relapse-prone population, again, enriched Wnt signaling. We see that this is a population which still nicely senesce, but the senescence isn't as stable as we are known to it. The samples start to reproliferate earlier, form colonies, and can therefore leave cellular senescence. When we now compare an inducible model where we restore SUVA function, you just saw this, compared to the clinical trial model, we see that the senescent condition can be retrieved in clinically failing lymphomas, and behind is Wnt signaling. So this allows us a novel view on senescence. There is no longer just drug resistance in the clinic due to apoptotic incapability, but there is a different type of resistance coming from apoptotically sensitive cells which fool via enhanced stemness and relapse. And that would be a target mechanism for selective senolysis. And that's what we did here. In a mouse model coming from the Campisi lab, INC4A induced means a promoter on in senescence. We induce herpes simplex virus thymidine kinase. This can be harnessed to poison the prodrug encyclovir and kill senescent cells. And that's the key experiment. So here 2 examples of never relapsed lymphomas. Black bars means upon chemotherapy, these mice are cured. There is no relapse. And if we add ganciclovir, cannot be any longer. They are anyway cured. But you may appreciate that there are black bars here. Mice relapse. But if we add ganciclovir, all of a sudden we see cure, and others don't. And it's now when we look at their senescence, their apoptotic capability, it's these lymphomas here with the retained apoptotic sensitivity but relapse capacity. These benefit from a selective senolysis, and here we use a different senolytic, fisetin. We can also lift them up, can convert relapse to cure. We looked at bortezomib. Now we are back to the initial 2 drugs, bortezomib, ibrutinib, and we're surprised to see that bortezomib in atramycin-induced senescence of human DLBCL cells has senolytic capacity. Here you see upon atramycin and DLBCL full-featured senescence with stemness, SASP, lineage aberration. But if you now add bortezomib, you attenuate, you buffer this phenotype. And if we, in addition to well-established senolytics, the dasatinib, quercetin, fisetin, navitoclax, use those and see that in atramycin senescent DLBCLs there is a senolytic effect. They kill these cells to a certain extent. It's ibrutinib and bortezomib which has the strongest potential, really good senolytics. And if we go into PDX models in mice, then we see what these agents can do. As single agents, bortezomib, ibrutinib, very little. In combination, also not too much. But if, in addition to cyclophosphamide to chemo, they are added, then we get tumor control, nicely closing the circle that our IMPROVER-CHOP trial may rely on the senolytic function of these 2 agents. With this, I like to conclude that We look at two terminal cell cycle exit programs with apoptosis and senescence. Senescence is believed to act as a backup program if apoptosis is no longer available. That may not be true. Maybe senescence is in several cells a primary response. Senescent cells undergo a T-cell recognizable immunogenic switch. They are treatment reprogrammed explicitly into senescence-associated stemness with Wnt activity as the cardinal pathway. Treatment failure, clinical failure, may remain apoptosis sensitive. I think that's clinically not very much appreciated. But these treatment failure apoptosis sensitive cells are Wnt high and are therefore susceptible to Wnt inhibition, or senolytics, which I have shown at the very end, which can turn indeed an imminent relapse into cure. With this, I am through, show you a lot of colleagues which have contributed to the work, like in particular to pinpoint Dimitri Belenki, Dorothy Fan, as those who did most of the work I showed today. Thank you.
Thank you very much.